So very good morning once again. Welcome back to the class. Dear students, we have already done some of the basic sorting algorithms, which are quite useful to sort. Say, for example, we have already seen the discussions about linear sort, about the quick sort, merge sort, heap sort, and insertion sort, selection sort. And we have seen that many of these mostly work with big O of n log n, and some of them, in worst case, work with corresponding time of big O of n scale. So we all have effectively got a basic idea of a sorting, and since last 2 semesters, you must be doing the sorting once and again in one or other form. But have you ever thought that can we think of doing sorting without comparing the values? Yes, it might sound a little strange, but yes, that's a fact that we just think of doing the sorting just by using various comparisons among these values, whether to find how many values are lesser than this and then compare these values, swap, select highest, select smallest, bring max on the top, etc. like that. But there are certain other ways also to do so. We call them as non-comparison based sorting. Yeah, something surprising, but you can imagine to do non-comparison based sorting also. In fact, we can say that we are going to do the same sorting now effectively without comparing the values. What does that mean? That we are going to have it as a sorting in linear time. Yes, as the word suggests, linear time sorting. So you can say this will mean the time complexity to be theta of n, or you can say not going to be more than linear time. Yeah, that is possible. Although when you say that we are talking of a sorting, we are not able to think that how can we do the sorting without comparing the values. Yes, wait. We are going to get its answer very soon. So I say effectively the sorting without this is possible. And in fact, there are 3 methods. One is called as a counting sort. Other is called as radix sort. And then we have similarly another third method, which we will be naming as bucket sort. So 3 alternates exist, but when I say like this, and I claim to have a theta of n, there is another theorem which proves that using comparisons, the sorting which we can do using any comparison methods, we can sort it on omega of n log n. And till now, we have already seen merge sort, heap sort, quick sort in average time or best time. All that takes normally n log n. Omega means a lower bound. So it says that on average, if I'm talking of worst case complexity, the worst case complexity for all these cases is a lower bound for n log n. So this is a lower bound for the worst case complexity. So using comparisons, worst case complexity is going to be omega of n log n. And we can always say that we have not seen any algorithm whose worst case is better than n log n. So this is the minimum time required. Sometimes worst case could be O of n square or theta of n square. But yeah, omega means minimum that much. So I'll say that go through this theorem, must read from the book so that you get a better understanding. I have always been saying that reading of the book is a must, and that will give you additional knowledge and conceptual clarity as well as basic foundation, which we are not able to cover during the classes. Well, this algorithm is a really big, very important subject, as well as it has a lot of relevant material, and covering of everything is not possible in the classes. So some of those things you must read, and at the same time, you will get a habit of reading from the books and understanding the standard language of book like Corman, which will give you a confidence, as well as you will be able to read and comprehend by doing self-learning also. So when I say omega of n log n, and then I claim theta of n complex t, so obviously we are talking of violating or improving beyond this theorem. But yes, it is non-comparison based. So non-comparison based in linear time we are targeting. And when I say theta of n, of course, it requires something special, because after a certain improvement, it's impossible normally to improve the algorithm's time complexity beyond a limit, as in this case. So always there will be a catch. And the catch is a star conditions apply. So in most of the advertisements, when we get some catchy advertisement, or when we get some kind of a special incentive, then there is always something mentioned and conditions apply. Yeah, here also conditions apply. So there will be all this possible based on some special characteristics of the data. Special characteristics, special properties of the data we can expect only in those situations such sorting in linear time will be possible. So whenever I'm saying a counting sort, it has some star terms and conditions apply, some star for radix sort, some star for buckets. So today's class, we are going to see both of these, and next class, we are going to do the bucket sort. Let's go one by one. And if I say that, yes, I'm going to now have the counting sort to be discussed. So let's start with the counting sort. It's a very simple algorithm. The only thing special about this algorithm is that we are going to do it non-comparison based. So that is the only something which you will find unknown to you. Otherwise, algorithm is very simple, but at the same time, because you are going to learn some new concept of non-comparison based sorting, this will give you a good idea how to have that thing possible. So the logic behind all this is simple, that effectively it says that first of all, the star condition apply. It means the values are, all values I will say, are in the range of 0 to k, and k is less than equal to n, where n means the total number of values, total number of elements, or total number of values, whatever you say. For example, if n is, let me just clear this. So if I say, if n equal to, let's say, 200, k could be something less than 200. Maybe let's say k is, if I say k equal to 20, this will mean 200 elements, but all elements are in the range of 0 to 20. Obviously means there are going to be duplicate values, many duplicate values, and the whole basis of this counting start comes from use of this concept. Well, effectively, the logic will be, main logic simply is that I'm going to count, somehow I am going to count how many elements are less than some value, how many elements are less than equal to, let's say, A1. If I say A1 is the first element, let's say, of my list, So somehow I will be able to find out how many elements are there. Let's say I come to know that 27 values are less than equal to A1, or I'll say not equal to also. For the time being, I will clear it as less than. So I say if 27 values are less than A1, say A1 is, let's say, 13, because the values are in the range of 0 to 20. So my A1 has to be something in the range of 0 to 20. Now I say if 27 values are less than A1, I can claim that A1 will be placed at guaranteedly 28th position. 28th position. Yes, this is what I want to do, and this will be possible. Well, something like this counting or finding the exact position, similarly we did in quicksort, where I brought my A1 to the correct position, and knowing that index, how many values are less than or less than equal to, there also be used, and then we were able to do the, but that was comparison based. Here the catch is it has to be done without comparison. So here you have to do all this without comparison. Well, again question mark comes, how? Well, don't worry, we are going to see that. So how to do? Let's have a look over this. Let's assume simply say n equal to 12. So I assume certain values, k being, let's say, 7. This means the values are in the range of 0 to 8. And total values are 12. So I assume certain values, let's say 3, 0, 5, 0, 3, 7, 8, 2, 0, 3, 5, 7, 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's assume, okay, remove the 13th value. So there are total 12 values. For the time being, I assume for simplicity that they are at index 1 to 12. So I assume n values in the range of array 1 to n. Although the safely it can be taken 0 to n minus 1 also, but simply taking it from 1 to n, that will be simply too easy to understand, as well as book also talks in the terms of 1 to n. So if you read the Corman's book, you will find it the similar match with my discussions. Otherwise, yes, normally in C programming, we always use array from 0 to n minus 1. So you can safely go 0 to n minus 1 also, not a big issue. Well, effectively now, the main logic says I'm going to simply count frequency of each number, frequency of each value. And the values are effectively in the range of 0 to k. So I will effectively count the how many times 0 appears. Then I will have count 1, how many times count 0, value 1, 0 value appears. Similarly, how many times value 1 value appears. And of course, we are going to have count k. Accordingly that. And because my all values are in the range of 0 to k, guaranteedly all values will get covered in this situation. Now, once I know this count, after that, I will say, well, anytime initially I have total n values. If I say that, for example, in this case, 0 is going to be 1, 2, 3. So my count array I will take. So this is my count array. So my 0 will be counted as 3 times. 1 I can see is effectively nowhere into this array. So I will say count of 1 is 0. count of 2 is 1. I can see here the count is 1. So similarly, I have 3 value. So the 3 value I can see is appearing once, twice, thrice. Again 3. Count of 4 is 0. Similarly, I say value index 5. You can see 5 is here and here twice. And similarly, I will have for 6. Similarly, I will have for 7 and maybe for 8 also. So that way I will have all values. Now, that gives me an advantage. Indirectly, I will say my final sorted array is guaranteedly going to be something like total 12 values, starting from 1, going up to 12, but as there are 3 times 0, first 3 values will be 0, 1, 2, 3. So I say, I can guaranteedly say they will be stored at index 1, 2, 3. This value doesn't exist. This will be guaranteedly in the sorted array at index 4. These values are value 3 is effectively 3 times. So this will be stored at index 5 to 7 and so on. So effectively at index 4, I will get value 1. I can easily see 3 values were 0. 1 appears 0 time, at 0 value appeared 3 times, 1 value appeared 0 time, and then value 2 appeared once. So I can say this, sorry, this is going to be 2. Let me just correct that, write it clearly. So this value will be 2. And after that, the value 3 is value 3. This value 3 appears 3 times. So I'm going to have it as 3, 3, 3 from index 5 to 7 and so on. So total values will be 12, but the values I can see easily will get arranged this. Well, it doesn't mean that you know that value 0 will be 3 times. So simply you put here initially at first 3 values 0. No, you have to copy the full value from your A array. And why I am saying this? Although for the you presently from, I'll say from array A, I have to copy all these values. Why I am saying this is A-double-R-A-Y. Why I am saying a copy? Because in real life, the values are not simply one value which we are going to use for our programming. They are full array, full structures, full records, where along with the sorting value, they will be having various other fields also. For example, I say student record. So student record has, say, rank plus many more fields. And let's say rank is in the range of 0 to K. So rank in the age of 0 to K plus their name is also there, roll number is also there. So in reality, the values stored when I said 3, or earlier I said it is a 30503. So it actually means 3 plus many other fields. 3, then name of the corresponding, then roll number, mobile number, etc., etc. Similarly, next value is with value 0 and then other fields, then value 5 and other fields, then similarly 305 and earlier we had 0378. So similarly 0378. So in real life, the students array is there and it has lots of fields And this value on basis of which sorting is being done on basis of some field, whichever field is used of on basis of, I'll say, some field which we normally call as a key. So if marks are being used for sorting, marks will be called as a key. If say roll number is used for sorting, roll number will be called as a key. In bank, account number is used, account number will be called as a key. So sorting on basis of whichever field, but along with that value, there are others also. So when your sorted array will come, in the sorted array, you will not have only zero stored at the initial position. You said that you are going to have a zeros initially 3 times 0, 0, 0 for 3 values, then 2 once, then 3 comes 3 times, and so, then 5 comes 2 times, like this. But all that doesn't mean that only 0 is just to be put here. It actually means this whole record is supposed to be at this position. So I have 0 plus name plus roll number plus mobile number and etc. etc. When I said second value is 0, it actually means this whole record will come to this position. Similarly, as we have seen, 8205357 20 and then 357. So I will say same values. We have this 0 also, and this will come to this position. So this whole record comes. Similarly, this whole record comes. Just have it here. Okay, let me just put it downwards. Yeah, so this. Okay, let me now have the right click. And so this is a full record corresponding to 2, and this whole will come to this position, and similarly others. So full record will be copied, but the position will be known to me. Position will be identified through certain mechanisms. So earlier, now I have said rough idea. So now let's go to clarity of how it will be done. So what we will be doing is initially generating the count. Say count of 0 will be 1 value. Similarly, count of 1 and up to k. So 0 up to k, the count gets known. Now I say, what I want is my values were 30. Once again, let's go back to the previous 3050378. So what I want is, now I will start from, for each AI, I would like to directly place. So my step 1 is count frequency of each value. And number 2 step is for each AI, directly place value in sorted array at the right index, at the corresponding index. How to do that? That means if I have value 3 here, I should know where the value 3 is supposed to be. Value 3 is supposed to be, value 3 I know is supposed to be at index, which we have just calculated. So value 3 is supposed to be at index 4. How to know that? This 4 actually came of adding up count 0 and then count 1 plus count 2. So effectively, for knowing where the value 3 will come, it will come to position next to summation of 0 to 2 values, 0 to 2 count. So for value 3, the position can be identified by this process. Now, that gives me clear idea that we require something like as a cumulative total or cumulative total of accounts is probably going to be useful. So that is the exact logic. So now it will be clear that how do we do. So I say I have 3, 0, 5, 0, 7, 8, and so and so. So initially, once I have found count array and I have calculated the values, say 0 is appearing 3 times, 1 is appearing 0 times, 2 is appearing once, 3 is appearing 3 times, 4 is appearing 0 times, 5 is appearing twice. Let's assume similarly for 6 also, it is 0 times. For 7, let's assume we have 3 plus 4, 7, 9. So there are 3 more values. So 7 appears, let's say 2 times, and 8 appears, let's assume once, or let's see previous data, and accordingly we can see how many values we have taken. 2, 0, 3, 5. So 7 appeared twice and 8 appeared once. So I'll just, yeah, we have the correct data available with me. So this is available. So I say effectively where value 1 will start is guaranteedly equal to this summation 3. Where value 2 will start, this is nothing but this summation is 4. Where value, so this is value 4 start. Then similarly, where value 3 will be stored is nothing but 4 plus 3, 7. 7 means after 4 up to 7. So after 4, after index 4, up to index 7. These are the positions for value 3. So effectively, that means cumulative count will be needed. And cumulative count, if I calculate above, the same counting array I can still use. I will say this is nothing but 3. Here also I will calculate the cumulative count. So this becomes this 3 plus 0, that is 3 itself. Although, because there will be no value at index 1, so this index will not get used at all. Then this will become 3 plus 1, that is 4. For value 2, index is coming to known. Then I will say 4 plus 3, that is 7. These are the effectively the, now I can say this is becoming the ending index for each value I, for value I. So effectively now count I is representing the ending index for value I. Simple. Similarly, 7 plus 0, that is 7 plus 0 equal to 7, because value 4 doesn't appear at all. Then I will say 7 plus 2, that is value 9. So ending index for value 5 will be 9. Then 9 plus 0 still remains 9. Then 9 plus 2 equal to 11 for value 7. And value 8, obviously index 12. So I had 3, 0, 5, 0, 7, 8. Let me just have the values. And 3050 378 20357 20357. So all 12 values are here. Now, once this count is ready, and I can see that these are nothing but ending indexes, this gives me a serious and simple business to do, that I should use the ending index to store. And because it's an ending index, I will start array backwards. Start AI from back. Means I will start from 12th value. From this is my index 12. And this is index 1. So I will start backwards. So I will say backward because last value is supposed to be at the last index. Relative ordering will be maintained. Stable sort will be ensured. If I start with ensured, if I start with the backward, if last value of AI stored at the ending index. It will be more clear once I go into more discussions in the a few minutes why I'm saying. But effectively, that means that now I have, using this value, I will say, I'm just for saving the memory space, I'm saying I have a sorted array, again 12 positions. I start with value this. This is from backward I start. 7. Where 7 is supposed to be? I know my cumulative index of 7. This is supposed to be index 11. So this is my index 11. This is index 12. Here the value 7, not value 7. To be precise, this full record will be copied at this position. Copy, not just value 7, because this may have many more fields. This value comes in. Again, you can see no comparison being done. I just know value 7. I go to the corresponding index 7 in my index array or count array and get the index position, and I go to this value. Then I come, and now because 7 might come again, I will remove this 11. 11 minus 1 I will make 10. So that next time whenever any value with 7 comes again, it should be stored at index 10, because 11 was the ending index for 7 and there could be multiple values with 7. Similarly, now I come to 5. The 5 is supposed to be at index 9. So I will go to index 9. That means this is index 10. So this is index 9. This whole 5 record will be copied here at this position. And I will subtract this and make it as 9 minus 1. That will become 8. So that next time again it comes, I know 3. So 3 will be at index 7. I will have index 7. 3 stored here, and this index will be changed to 6. Then 0 comes. 0 stored at index 3. So 0 will be stored here, and this will be reduced to 2. Now 2 comes. 2 will be stored at index 4. So 2 will come here. This index will be again decreased to 3. 8 comes. 8 is at index 12. So 8 will come here. This index will be further decreased to by -1, although it will never get used. Now see, 7 comes again. So this 7 is supposed to go to at index, which was earlier 11, has been reduced to 10. So 7 value will come at this place. Not only 7, but a full record. So this full record, let's say R7.2, this is record R7.2, and this was our record 7.1. So R7.1 is here, R7.2 is here. Again, why I am stressing and giving the name of 7.1 and 7.2, their relative ordering is ensured of where key 7 is maintained. That we are able to maintain, and this is what exactly is called as the corresponding stable sort. This is what we mean by stable sort. So when we said a stable sort, effectively means that if there are 2 records or multiple records with the same value, like one is this, one is this. So I have 2 records, each having key as a 7, but other fields may be varying. Then if this particular record was before this second record, or if R7.2 is on the left of R7.1, I say if R7.2 is on the left of R7.1 record, both have same key, so that is the first condition. If R7.2 is on the left of R7.1 in the original array, then the same order must be maintained in the sorted array. Same relative order must be there in the sorted array. And if we are able to do so, then this is called as a stable sort. And why we are again talking of all this? See, just remember that, say you have JEE ranking to be announced based on marks. So you know, if the total marks are same, let's say total is the same, if a total marks scored by you are same, then their ranking will be decided based on maths. If the math marks are also same, their ranking will be decided based on physics marks, then based on chemistry marks, and so and so. Now assume that you have already sorted the marks on basis of chemistry. If you have already sorted on this basis, after that, if you sort, or I'll say if they are already sorted on basis of, let's say, this order, I'll say, if they are already sorted on basis of these some way, now they are sorted for the total. If the total is the same, then their previous sorting based on math marks should not get disturbed. Previous sorted order, sorting relative order based on the math should not get disturbed. Otherwise, your rank will get disturbed. Based on M should not get disturbed. And if math was also same, then the previous ordering based on P should not get disturbed. Only then I will be able to have correct ranking announced. So this is why we always focus on saying stable sort. Hence, stable is important. So that is why we have done this. As a Zoom recording might get completed, let me just stop here and start the new class. And for a few more minutes, we will discuss. Just please let me stop this and let me stop sharing and let me